Hola, buenos días. Bueno, bienvenidos a una nueva edición de los coloquios de Iparcos. La próxima tendrá lugar el 15 de diciembre y va a ser sobre astrofísica. Será Itziar Arechaga, del Instituto Nacional del INAOEP, no sé exactamente, no recuerdo cuáles son las siglas, de México. Y será, como digo, el 15 de diciembre, que será el último de este año. Y no va a ser aquí, va a ser en un aula de químicas, os lo aviso para que, por supuesto aparecerán los anuncios, pero para que lo tengáis presente que va a ser en un sitio inhabitual. Y dicho todo esto, nuestro orador hoy es Andreu Font-Ribera, del Instituto de Física de Altas Energías. Y bueno, pues que el título lo tenéis ahí, nos va a hablar de la expansión acelerada del universo, en particular con un instrumento, analizado con un instrumento en particular, que es DESI. Y Andreu hizo la tesis en el Instituto de Ciencias del Espacio en Barcelona y después estuvo de postdoc tanto en Zúrich como, bueno, después fue a Berkeley y después estuvo en Londres, en University College, que estuvo como profesor durante unos años, con una fellowship bueno, creo que se llama Rutherford Fellowship, para después ya integrarse en el Instituto de Física de Altas Energías con un contrato de Ramón y Cajal, y en este momento quizá, pues como el dinero es el dinero, pues merezca la pena señalar además una cuestión de prestigio, y es que ha obtenido hace ya unos años, hace 2 años o 3 años.
Hace un año y medio.
Hace un año y medio, una ERC Consolidator, así que si queréis contratos, yo creo que, bueno, sin más y aparte de bromas, vamos a dejarle a Andreu que nos hable de la expansión del universo. Muchas gracias.
Primero que nada, pedir disculpas que la charla va a ser en inglés, porque primero que las diapositivas lo están y que me cuesta un poco dar charlas en castellano, pues no estoy muy acostumbrado. Pero la introducción puede ser en castellano. Muchas gracias por la introducción y por invitarme a dar un coloquio. Es un placer estar aquí. Y veréis que la charla he intentado hacer un poco de equilibrios para intentar que los estudiantes y la gente que trabaja en otros campos puedan seguir la charla, pero al mismo tiempo que de vez en cuando los expertos, que hay unos cuantos en la sala, pues también estén interesados. Así que si en algún momento veis que os habéis perdido, no pasa nada, que en un par de diapositivas volveréis a estar en la charla. También antes de empezar, si tenéis alguna pregunta técnica sobre las diapositivas que en aquel momento puede ser relevante, podéis levantar la mano e interrumpirme, intentaré estar al loro. Si es un comentario o algo que queréis añadir, lo podéis esperar al final de la charla y tendremos tiempo para hacer preguntas. La charla debería ser unos 45 minutos, así que habrá tiempo para preguntas. Okay, so let's start. So I'm going to be talking about the expansion of the universe, and in particular how to study it with this dark energy spectroscopic instrument. So why looking at these galaxy surveys like DESI? The main reason is because if we study the distribution of matter in the universe as a function of scale and as a function of time or as a function of redshift, we can learn about many things, and we can also try to address some of the most important questions in fundamental physics. So as an example, you can see in this diagram from the Snow Mass report a couple of years ago, where you see some of the big questions, how can they be addressed by looking at different probes that look at different scales. So you can see large scales on the top and small scales at the bottom, and also as a function of cosmic time. So we are sitting here at redshift 0, here at the right is very high redshift, and you can see that we can address many different open questions in physics by looking at different cosmological probes. Right. The focus of this talk is going to be mostly dark energy. So that's something that can be studied mostly at low redshift, and that's why galaxy surveys are relevant. There are other probes that are more beneficial if you study them with a cosmic microwave background or other types of cosmological probes. I will briefly mention also neutrinos, dark matter, and modified gravity, but the focus will be mostly dark energy. So the talk will be roughly split into 3 parts. First, motivation for why we're trying to do this and what are the main science drivers for this quest. The second one, that is actually the longest, will be trying to actually look at cosmological constraints that we can learn from galaxy surveys that we have now, and in particular, which are the key probes that help us understand these different questions. And finally, this is more like the advertisement, because this is like the work that we are currently working on with some people also in the audience, this dark energy spectroscopic instrument. you will not see any, private result that has not yet been published. Unfortunately, we're not allowed to show those, but we will show at least, I will show at least some interesting preliminary data that hopefully gets your attention. Okay, so the first science goal, as I mentioned, is dark energy. And now, after 25 years or so of the detection of the accelerated expansion of the universe, now we have many different probes all pointing towards the same fact, that the acceleration of the universe, the expansion of the universe is actually accelerated. And we don't know what caused that, and we use this generic name of dark energy to basically say something that we don't understand that drives the expansion to be accelerated. So it's more like a placeholder. And if we want to understand better what is causing this accelerated expansion, what is the nature of this dark energy, one of the best ways to do that is to provide very accurate measurements of the expansion of the universe as a function of cosmic time. So here on the right, this is the forecasted version of how well DESI, this instrument that I will be talking later today, how well we're going to be measuring this Hubble expansion as a function of time. So you can see that you cannot see the pointer anymore. Oh, yeah. So you can see that at high redshift, the universe was decelerating as you go to lower redshift, but lately dark energy has caused this expansion to now accelerate again. And we're trying to study this by measuring very precisely this expansion of the universe as a function of redshift. One of the things that we will look is at what is the equation of state of dark energy. And you can see this W that is basically the ratio of pressure over density, and different models for what dark energy could be make different predictions for what should be the equation of state of dark energy. For instance, the simplest model is the cosmological constant, and in that case, W is equal to -1, and it doesn't change. But there are other models that propose that W not only will be different than -1, but it will also change with redshift. It will be dynamical. So by putting tight constraints on this expansion, we will be able to tell the difference between some of these models. As I mentioned, sometimes we'll try to parameterize this W and W prime as how this equation of state of dark energy changes, but don't worry about what it actually means. It's basically how well DESI will do in red versus what we have now in blue. We'll considerably shrink the parameter space of what possible models are allowed by the observations by having these measurements of the expansion. So a part of the expansion of the universe and study dark energy, we can also use these maps of galaxies to study deviations of general relativity, so modifications of gravity. And it's important to take that into account because it's also one of the possible explanations for why is the universe, the expansion of the universe accelerated. One of the explanations could be that maybe we need to modify gravity. And modified gravity not only changes the expansion of the universe, but it also changes the growth of a structure, how galaxy groups grow with time, because that depends on gravity. So providing measurements not only of the expansion, but also of how fast or how slow the structures in the universe grow will be very important to tell the difference between different models of dark energy or different models of modified gravity. So here on the right, I'm just showing as a function of redshift how well basically DESI will measure this growth rate, how fast the structures grow as a function of time. And I'm just showing a few lines that are not particularly relevant, just some modified gravity models that predict different evolutions for this growth of structure, just as an example for some models that could potentially be ruled out by the end of DESI. The third motivation, that's one of the motivations that I'm most excited about, is the possibility of measuring the masses of neutrinos using cosmology. So you probably all know that neutrinos are the lightest particles in the standard models. We thought for many years, well, they thought, I wasn't even born, that they were massless, but in the last years, it has been shown that they have, at least some of them are massive, but we don't know what is the mass of these neutrinos. And because they have an impact on how the matter is distributed in the universe on small scales, it also has an impact on these galaxy maps. So by looking at these distributions of galaxies in the universe, we will also be able to learn about how massive these neutrinos are. And what I'm showing here on the right are what are the possible values for the 3 neutrino masses. We have 3 families of neutrinos, so there are 3 different values of this mass. And depending on what is the actual hierarchy of the neutrinos, and this is probably going into too much detail for the non-experts, but you can have different ranges of these values, and basically DESI will provide a very tight measurement of the sum of the neutrino masses of 0.02 electron volts for the experts. For the non-experts, that's very good. So that's the idea. Those are the three main motivations for why we're trying to do these experiments. We want to learn about dark energy, we want to learn about modified gravity, and we want to be able to put measurements of the mass of the neutrinos. Okay, some technical difficulties. Okay, great. So how do we do this? Right, so this was just a motivation of which were like an idea, some flavor for what type of science are we trying to go after. Now I'm going to try to spend a little more detail and going a little bit slower on how exactly we do this from these galaxy maps. I'm going to start by talking about the probe that we think is not only more robust, but also the one that has already provided very, very good cosmological constraints. There are other probes that are a little bit more novel, less mature, but BAO, these baryonic acoustic oscillations, has already been in the market for 20 years or so, and it's working very well. And then I will present some results from the Sloan Digital Sky Survey, or SDSS, that has been, until now, basically the main spectroscopic galaxy survey to be used for cosmology, and also for other science. So if there are astronomers here that do not work on cosmology, but work on stellar evolution or galaxy formation, SDSS is also a very powerful data set. So, sorry, right. So if you are an astronomer that you have taken some images of a galaxy and you're able to measure the redshift of that galaxy, what you usually say, or you can say things like, this galaxy is very far away, it's at redshift 1.5, therefore is at, I'm going to make this up, at 5 gigaparsecs from us. Right? Light will take many, many millions of years to arrive here. This connection between redshift and distance, or between redshift and travel time, you need to assume a cosmological model. So if you have a cosmological model that tells you how the Hubble parameter changes with time, you can then compute what is the distance to that galaxy, or how long did the light travel to get here, because we know the speed of light, right? But that's really not what cosmologists are more interested about. We're usually trying to do the opposite. What we would like to know is we don't want to assume a model, we want to learn about this model. So what we want to do is we want to have measurements of the distance to some redshifts. Because if we have many measurements, sorry, this is becoming, here. If we have many measurements to the distance to galaxies that are at different redshifts, we would then be able to put very strong constraints on some of the components, energy components in the universe that set what is the evolution of these Hubble parameters. So for instance, we would be able to tell how much radiation is in the universe, how much matter, what type of matter, but also how much dark energy is there, whether the universe is flat or is not flat. All of those things have a different evolution with time. The density of those components depend differently with time or with redshift. So if we had very precise measurements of h of z as a function of z, we would be able to tell apart all these different components of the universe, right? So that's one of the main goals of these studies of expansion as a function of time. And here from the Planck satellite, we know from a different probe that roughly 70% of the energy content in the universe is in this form of this dark energy, and 27 or so percent is in the form of dark matter, matter that does not interact with light, and then roughly 5% is in ordinary matter, or what we call baryonic matter. So I was saying we want to measure distances to galaxies that are at a certain redshift, but this is actually really hard. We don't know in astronomy in general how to compute distances to objects. When they're very nearby, we can use some techniques that has been used for hundreds of years that are basically geometric ways of getting the distance to the stars, like for instance using parallaxes, the fact that when the Earth moves around the sun, it sees the positions of some stars a little bit displaced, and from that you can infer the distance to the stars and so on. But in order to go to higher and higher redshift, you really have to start being creative. There are some ways, like looking at the Cepheid stars, that are some variable stars. But once you go outside your galaxy and you want to go very far away, it gets really challenging to getting measures of the distance to these objects, because we just don't know how far they are, right? So one of the best ways to do that, and it was how this accelerated expansion was first discovered, is to use what we call standard candles. And in particular, a particular type of standard candles called supernovae of type 1a. So what are these standard candles? Is well, if we know how bright a given object is, how many photons per second it emits so that we can energy, and we can measure some apparent flux with our telescopes on Earth, we can infer how far this object is, right? So that's a big if, because we don't really know very well how bright a given object is. But if we could know that, we would be able to place the distance to that object from Earth, and then that's it. We know the distance to the object, we can constrain dark energy and others. So supernovae are not always perfectly standard, so they are not always as bright as the others, but they are fairly standardizable, so we know how to use this technique to calibrate distances. However, we can only go that far with supernovae, and it's also good to have a complementary probe. So apart from the standard candles, what I've been working on and what I'm going to be talking during this talk is to use what we call the standard ruler. So the idea here is very similar, is that if we knew the actual physical size of an object, and we can measure it from Earth, what is the angular size, we will be able to tell just by simple trigonometry what is the distance from this object to us, right? And of course, here the question is like, which object? Like, is there an object that we know exactly what is the size of that object? And unfortunately, the answer is that not quite. It's not that simple, but we have alternative techniques to effectively have a standard ruler that we can use, and we can measure it at different redshifts and measure these distances to these different redshifts. And by the way, a few years ago when I was giving this type of talk, that would be it. But since 2015, 2016, now there's a third way of getting distances in cosmological distances, that is to use gravitational waves. So far it only happens once, but in the beginning it was very exciting because after 1 year we saw one. Now we have been like 8 years without seeing one. But hopefully with the advances of the gravitational wave detectors, we'll get more and more and more of those, because we have seen about, 100 gravitational waves events, but most of them do not have an optical counterpart. So we hear with our gravitational wave detectors that a collision has happened in the universe, but we don't know exactly where. So that doesn't help us. There was only once, there was a binary neutron star in 2016 that we were able to identify its optical counterpart. We were able to measure its redshift, and because the strength of the gravitational wave collision is well known, because it's using general relativity, you can compute it, then we were able to infer the distance to the galaxy hosting those binary neutron stars. Now, the main difference between this and the others is that in this probe, it's very easy to measure the distance. It's very difficult to measure the redshifts. While in the other two probes, it's very easy to measure the redshift, but it's actually difficult to measure the distance. But that's something that in the future maybe will play a role in this business. So far, it's not really playing an important role yet. So what is this magic standard ruler that I was mentioning? This is what we call the baryon acoustic oscillations, or BAO. The idea is that in the very early universe, above redshift 1000 or so, the universe was very hot, was very dense, and most of the universe basically behaved as a plasma. There was baryons that were coupled. There was basically hydrogen atoms, not atoms because there were protons and electrons floating around, and they were coupled to the radiation, and they behaved like a plasma. And because gravity had there were some overdensities and underdensities in the density field, gravity caused some acoustic wave to propagate. There were some regions that were denser, so there was more pressure, so that bounced back and so on. And there were acoustic waves propagating across the universe. So here's just an animation by Daniel Eisenstein, who's one of the main developers of this technique, that just shows in a simplified universe where there's only one overdensity that has both higher density of baryons and higher density of radiation, what happens to that overdensity with time. So it propagates like a wave, an acoustic wave, and at some point the universe gets colder and colder, it gets less dense, and at that point these acoustic waves stops, because we are for the first time able to create neutral hydrogen atoms. So electrons and protons are captured, and then they stop interacting strongly with the light. So light just travels through, and that's what we see as the cosmic microwave background. And that means that there's a particular scale, that is how far did those acoustic waves travel between the Big Bang and the moment of recombination at this redshift 1000, where the atoms form for the first time. So that's our standard ruler. It's this acoustic, the sound horizon of those acoustic waves, and we know how to compute it fairly well. It depends only on a few parameters, like the radiation density or the matter density or the baryon density, that are actually very well measured from the CMB. And with some relatively simple atomic physics and these elements, we can predict the size of this ruler very well. It's roughly 150 megaparsecs, so very large. So this baryonic acoustic oscillation let me see if the pointer, there you go. So these oscillations are also responsible for these features that we see in the power spectrum of the temperature fluctuations in the cosmic microwave background. And here I might lose some of the audience again. Apologies for that. I'll hope to bring you back soon. But what I show here is the fluctuations in the temperature where we point to different parts of the sky by the Planck satellite. And what we see is that pretty much everywhere in the sky, the temperature from this cosmic microwave background is about 2.7 Kelvin, but there are very small fluctuations around this mean temperature. And what this shows is the characteristic amplitude of these fluctuations as a function of scale. And these beautiful features that you see here are caused by these acoustic waves. So they're related to the harmonics of these waves and so on. All I'm showing is that, for now, maybe like a couple of decades or so, we have seen these peaks, these oscillations in the cosmic microwave background, and the idea is to do the same thing in the distribution of galaxies. So you will understand this plot a little bit better in a few slides, but what I'm trying to show here is that from this SDSS survey that I mentioned in the beginning, we were able to measure the size of this ruler very precisely, sometimes with a precision of 1% or 2% as a function of time. So we have 6 different measurements, actually 7 if you include the purple one at the end. That's the one I've actually been working on most in my career. We have 7 measurements of this size of this acoustic ruler as a function of time. So that allows us to constrain the expansion of the universe very well. And what we are after, we are trying to detect this particular feature. We call it the BAO peak or the BAO bump. There's this particular feature that is an extra correlation around at this 150 megaparsecs in the correlation function of galaxies. So if you have a given galaxy at some position, there's an excess probability of finding a second galaxy at 150 megaparsecs because of these acoustic waves that I mentioned at the beginning. Okay, so we have this, let me try to, okay. So we have this standard ruler, this magic ruler that we can then use and measure as a function of redshift using different galaxy samples. So the idea is that now we'll have catalogs of millions of galaxies at different redshift. We will look for this excess correlation. And what we will be able to do is measure the correlation as a function of angle. We will see that we have 2 galaxies that when you look at galaxy pairs at a particular angular separation, there will be an excess correlation. And then we see this excess correlation. Let me try to use my second pointer. There you go. So we will measure an angle, a particular angle that has this extra correlation between the positions of galaxies. And because we know the size of the standard ruler, this RD, the sun horizon, we will be able to infer what we call the angular distance to these galaxies, the angular diameter distance to these galaxies. And then there's another thing we can do. We can imagine not only looking at correlations as a function of angle in the sky, but also correlations as a function of line of sight separation because we have redshift for these galaxies. So we can look whether there's an excess correlation at a given redshift separation between 2 galaxies. And we can measure these basically redshift and velocities are indistinguishable. We also measure this excess correlation, and with some basic formula, you can show that this tells you I'm going to try to use both pointers at the same time. Well, you can see this delta V BAO. This tells you not a measurement of the distance to that redshift, but a direct measurement of the expansion rate at that time. So we have 2 different ways of learning about cosmology from these measurements. We can try the third pointer. Let's see if... Yeah, it seems to work better. Great. So by doing these measurements of BAO as a function of redshift, both by looking at the angular correlations and in the line of sight correlations, we have very complementary and very strong constraints on the expansion of the universe. This is again only for the experts, I'm afraid. There's one point later on where I will also use another probe that we call redshift space distortions. Actually, I've already used it in the motivation slide in the beginning, so don't worry if you get lost in this slide. But the idea is that there's another thing we can use. It's in the distribution of galaxies. There's another effect that is very powerful. That is the fact that we don't measure distances directly to these galaxies. We measure redshifts. And the redshifts tell us about the expansion of the universe, but it also tells us whether that particular galaxy is moving towards us or moving away from us just because of peculiar velocities. Maybe that galaxy is next to a very large galaxy, so it's moving towards that one. Or maybe that galaxy is near a big void where there's no galaxy and that galaxy is moving away from that void. So the surrounding density also causes an extra kick in the velocity of the galaxy, so an extra redshift difference. And we call those redshifts distortions. So when we look at the distribution of galaxies, they become also anisotropic. So the correlation is not the same along the line of sight, but in the transverse direction. So when we look at this anisotropy of these galaxies, the shape, instead of being circular, it will be, a little bit squashed. So this is the measurement of correlations as a function of transverse and line of sight separation from these galaxy samples. And you can see that they're not symmetric, they're a little bit squashed. And the strength of this asymmetry tells us about the growth of a structure, because it tells us about the velocity amplitudes for these galaxies, and that also depends on gravity. So when I was talking in the beginning about these constraints on modified gravity, they come from this type of measurements of the velocity power spectrum from the redshift space distortions of galaxies. And this will also be important later on when we talk about neutrino masses. But that's probably one of the very few slides that is about redshift space distortions and not BAO. Okay, so I hope that more or less the idea that there's this technique called BAO that we can use to constrain cosmology and that we can extract from these galaxy maps. I hope that I went across the audience. Let me now show you some results from the Sloan Digital Sky Survey. So SDSS, or the Sloan Digital Sky Survey, actually goes back in time until to the 90s. And for 20 years, there were different versions of the survey that had different goals, sometimes looking mostly at supernovae, sometimes looking at galaxies, sometimes doing other type of astrophysics. But over 20 years, it collected a lot of galaxies, millions of galaxies. And in 2020, 2021, we worked on the final legacy document. It was basically the last paper talking about cosmology from SDSS, where we put together all we have learned over these 20 years. So I'm adding the pictures not only because it's an important paper that we wrote, but also because we wrote it during COVID lockdown. So it was very useful for my mind to go back to sanity, to have these weekly telecons with these 5 people, and it created a bonding. So the idea is to use these different galaxy maps collected over 20 years. And what I'm showing here, the Earth is sitting at the center of this sphere. Sorry, wrong pointer. There you go. So we are here, and we are looking back in time. So different colors show the positions of different types of galaxies. So near us, we have the galaxies obtained earlier on from SDSS 1 and 2 in the 90s and early 2000s. So those are galaxies that are a little bit near us, so relatively to the others. So it allows us to study the universe not many years ago, only a few millions and millions of years ago. But then as you go to farther and farther distances, you're studying the really early universe, right? So some of these data points, in particular, the great data set. Oh, we have lost pointer 3. This is bad. Okay, the white data points at the edge of this sphere, those are quasars that are some of the brightest galaxies that we can observe in this survey, and it allows us to study the universe when it was only 25% of its current age. So really young universe, and we can measure the expansion of the universe at that time by looking at these BAO peaks. So you can see here again the different BAO detections from the different tracers, and even at very high redshift using the quasars, we can get a 2% measurement of the expansion rate at that time. So it's really impressive that at some point, we knew better the expansion rate of the universe when it was 25% all than we knew the expansion now. Now it's no longer the case, but it's still quite impressive. So what do we learn from this? I'm now going to be showing some of these cosmological constraints. I'm going to try to go slowly in case some of you in the audience are not very familiar with this type of parameters. But the idea is that we can constrain some of the parameters I was describing earlier that tell the different components of the universe and so on. One of them, the most important one, is this omega m. So omega m here, oh, there you go. Omega m here is the matter density in the universe. Another one is sigma 8, is the amount of clustering, so the amount of structure in the universe, how much matter has been accumulating into superstructures and voids and so on. And then on the right, I'm also showing H0, that is the expansion rate of the universe now at redshift 0. So here I'm showing constraints from some surveys. For instance, I've been talking about Planck, the CMB satellite, those are in gray. Then in the vertical line here, you're seeing some results from the latest compilation of supernovae from the Pantheon survey. Here in the horizontal line, here labeled Rees et al., is a measurement of the expansion rate using a different technique called the distance ladder, and we will be talking about this later on today. And in blue, you see the constraints from SDSS, and those include BAO, but also the redshift space distortions measurements that I mentioned at some point. That's why I included at the last minute that slide, because these results are not just BAO, they also include the redshift space distortions. Otherwise, we wouldn't be able to measure sigma 8. This is for the experts. Good, so what do you see here? You see that there's a very good agreement between the constraints from SDSS in blue and the constraints from the CMB in gray from Planck. You can also see that a different survey called the Dark Energy Survey, DES, has a very different type of galaxy survey. They also measure these very elongated bananas, but they are also in agreement with the results from SDSS. But another thing that you see here is that both Planck and SDSS are in tension with the measurement of the local expansion by the distance ladder, and we have a couple of slides talking about this in a few minutes. Another thing that you might ask yourself is like, well, if we had the results from Planck that are tiny, tiny gray contours in this plot, why bother doing galaxy surveys if all you're going to do is add big blue contours that are not competitive with Planck, right? The answer to this question is in the next slides. That is that these constraints are from what we call the vanilla lambda CDM model, or basically a model that assumes several things about the universe. It assumes that neutrinos are massless, and we know that's not true. It assumes that the universe is flat, and it might or might not be. And it assumes that dark energy is a cosmological constant. If you break any of these assumptions, then suddenly Planck is really not very good at constraining those things. So we're going to look through those. We call them extensions to flat lambda CDM. So the first extension that we want to look at is the curvature of the universe. The equations of general relativity allow for the universe to not be flat. It allows to have curvature being positive or negative, and we parameterize this with this omega k parameter. It tells, so if omega k is 0, the universe is flat. If omega k is different than 0, it means that it's curved or with an open or closed universe. So if you only have the CMB data in gray, you are not very good at measuring these things because most of the information is coming from very high redshift, and curvature changes how the universe expands between then and now in a way that is degenerate with other parameters in the model. So you have these very long elongated contours in gray, but as soon as you add supernovae in red, or as soon as you add BAO data from SDSS in blue, you really measure now very well that the curvature of the universe is either flat or very, very close to flat. Right? So this is one example that is quite clear of why is it important to combine different cosmological data sets, because they have different degeneracies to some of those parameters. Another example is the equation of state of dark energy. So remember I was telling you about this W, that is the ratio of pressure to density in the dark energy component. In the cosmological constant model, this is equal to W equal minus 1. This is the dotted horizontal line at W equal minus 1. But if you allow for W being different than 1, then Planck, again, is not very good at measuring this. This is the gray contour that you see here are the results from the Planck CMB dataset. You could argue that the other ones are not very good either at measuring those because they also have very elongated bananas. But the good thing is that because they are probing different redshifts, the degeneracies between these parameters are very different. And the only place where the three data sets touch each other is exactly at the W equal minus 1. You might argue it's the most boring possible answer from this experiment, but everything is pointing to dark energy being a cosmological constant or something that looks very much like a cosmological constant. So the last extension that I want to show is these massive neutrinos. I mentioned that we know from particle physics experiments called neutrino oscillations experiments that the sum of the neutrino masses cannot be 0. So we don't know whether the electronic neutrino or the tau neutrino or muon neutrino are massive, but we know that the sum of their masses cannot be 0. So we have a lower limit on the sum of the masses. The interpretation of the lower limit depends on some technical details of physics of neutrinos called the hierarchy, but we don't have to get into that. on the other hand, the CMB is also sensitive to neutrinos. If the models that we use to feed the temperature data in the cosmic microwave background depend on the mass of the neutrinos, so we can constrain and put limits on those parameters. But again, there's some internal degeneracies in the CMB data alone that cause these gray contours being elongated. And when you add low redshift data from supernovae or from BAO, again, you're able to measure better the matter density omega m, and because of that, measure also better the mass of the neutrinos. So we are still a little bit far from those limits, but not that much far, right? The second one, let's see if pointer 2 suddenly has recovered. There you go, see? So this one, it's basically 0.1, it's here, right? So we are getting quite close to being able to exclude one of the two neutrino hierarchies. And we expect that in a few years, either from DESI or from other cosmological surveys like LSST or Euclid, we will actually be able to measure these measurements with a precision high enough to either detect the mass of the neutrinos or distinguish between the hierarchies and so on. So if you're interested in neutrino physics, cosmology is going to be a relevant player in this topic in the next few years. So I also mentioned this Hubble tension, this problem about the current measurement of the expansion rate of the universe. And it's a little bit complicated because, you know, you could argue this is one of the main parameters that we want to measure. How fast is the universe expanding? And we just don't know very well. It has been very controversial historically. You know, 50 years ago, there were big fights over an order of like a factor of 2 between different groups of what was the expansion rate of the universe. Then in the 2000s, we thought we had solved the problem, and it was going to be around 70 kilometers per megaparsec, kilometers per second per megaparsec. But now, as the error bars of the different experiments got smaller and smaller, it started to become clear that if you look at the expansion of the universe using what we call the local distance ladder, meaning measurements of things that are near us, without assuming a cosmological model in principle, you get these measurements that are relatively high. So those are the Cepheids measurements that you see in blue. I have no idea what's happening with the pointer, but one of them. Yeah, there you go. So while on the other hand, if you infer the Hubble expansion using CMB data under the assumption of a cosmological model, we measure these measurements in black CMB, and they're becoming very, very much in tension. So this is a relatively old compilation. I should update this plot at some point, but basically says that there are 3 categories of results so far. There are several cosmological probes that really prefer a low value of H0, around 67 or so. Then there's the distance ladder that I was showing in the previous plot in blue that really prefers a high value of H0. And then there are a few of other probes that, you know, are consistent with both. They have large error bars. They're not able to tell the difference between the two. But you could argue what could be going on. You could say, well, maybe there's a statistical fluke. Maybe we were just unlucky, and, you know, maybe at the end things are consistent, and with more data, things will agree. But this is now a 5 sigma discrepancy between those two measurements. These things shouldn't happen by luck. So I would scrap that one. It could be systematics in the CMB data, maybe. It's a very complex analysis, so why not? It could be systematics in the distance ladder. I'm not an expert in Cepheids or supernovae, but it's also a challenging measurement. Or it could be a problem with the model that we used to go from the CMB data to this constraint, so a problem with flat lambda CDM. I will argue that we have cosmological probes that do not assume cosmological constant and still prefer a low value of H0. So they vary equation of state of dark energy and still find low value of H0. Still in very much tension with the other measurements. We have measurements that do not use any CMB data, just use BAO and big bang nucleosynthesis, and also prefer a very low value of H0. So I don't think this is the answer. It has to be something else. So I'm a bit, I think just in case, I'm going to skip those 2 slides that are a bit technical, just showing these measurements of H0 from BAO. The summary is what I was mentioning, that it cannot be statistical fluke. It cannot be systematics in the CMB data because we have other ways of measuring this without CMB, and still we recover this low value of H0. I don't think it's a problem with flat lambda CDM because when you allow for curvature or you allow for dark energy not being cosmological constant and so on, you still have that tension. So it's either systematics in the distance ladder, or another option that in the last few years has become quite attractive, and a lot of theorists are now writing papers on possible solutions, is that all the experiments on the left, they assume the physics that set this sound horizon. These acoustic waves that I was mentioning in the beginning, how far did those waves travel in the early universe? They assume things that you would imagine, it's not that complicated physics, it's relatively easy physics. But if there was some special fluid in the early universe, or there was some really strange property or one of the fluids at that scale, you could change maybe the sound horizon. So you might have heard about early dark energy or other models that basically they change the sound horizon at early times without breaking the cosmology at late times. So I'm not sure personally whether that's the actual solution, maybe just systematics in the distance ladder, but I think it's becoming more and more clear that those are the two options. Either we need to change the sound horizon or it's systematics in the distance ladder. Okay, so we finally reached here's where I'm going to start talking about my book. So this is a dark energy spectroscopic instrument, and it's sometimes, I don't know, some people think it's cheating. I think it's okay. There was a video that was made by the collaboration that explains the instrument beautifully. So why would I try to explain it instead of just playing the video? So let's see if the video works. If not, I will have to explain the instrument.
Light first reflects
can
off
you...
the telescope's 15-ton primary mirror. Then onto its
It's just 1 minute.
Light first reflects off of the telescope's 15-ton primary mirror, then onto its 6 large lenses that ensure DESI maintains a wide, highly focused view of the sky, covering an area about 38 times larger than the full moon. These lenses are housed in a device that can be adjusted within millionths of a meter to preserve the alignment of those lenses. After passing through the set of lenses, the galaxy's light reaches fiber optic cables in DESI's focal plane at the top end of the telescope. 5,000 robotic positioners, each carrying a single optical fiber, are programmed to move to pre-selected sequences of galaxy targets. This automated dance of robots allows DESI to target sequences of thousands of galaxies at a time. The optical fibers, which serve as DESI's eyes, send the galaxy's light down the length of the telescope to 10 spectrographs.
Okay, so I hope this was clear or useful. By the way, it was great to have these little robots, because in the previous version of the survey that I was mentioning, this SDSS, there were actually people plugging 1,000 fibers, optical fibers, by hand on a metal plate, and they had to do this 10 times per night. So it was a crazy amount of work, just plugging fibers and so on. So now there are some robots that work for us, and this is helping us a lot. So in case the video didn't work, I had some backup slides. So this is the cartoon of the telescope, but I'm not going to go through that in detail. Just highlighting that these optical lenses are massive. They're huge. They are super tall and super heavy. They were aligned at UCL, where I was a few years ago. And also that this focal plane has 10 cameras. Here you can see them, they call them the GFA cameras, and they were actually designed and constructed by a consortium of institutes here in Spain, including IFAE, but also including CIEMAT, the Institute of Física Teórica in Madrid, and also the Institute of Space Science in Barcelona. So this is our small contribution to the instrument. And finally, just showing that the picture of the instrument really looks like the cartoon, so it's a good cartoon, the person who drew it. And here is the description of what are we going to try to look at. We're going to try to look at around 40 million galaxies and quasars, distributed again over a wide redshift range. So some of the galaxies are going to be sitting near us. We're going to observe 13.5 million of those bright galaxies that we see near us. Then we're going to be looking at another type of galaxies called the luminous red galaxies, the emission lane galaxies in purple. Those are the ones that are more common, 60 million of those. And then these quasars at very high redshift that we will use to study the expansion of the universe with the quasar population themselves, and also using a technique called the Lyman alpha forest that is basically my field of expertise. So this is great. We will collect these 40 million galaxies over the next 5 years. Actually, we already started 2 years ago. We are half finished, and we're going to use that to learn about cosmology. So to make it a little bit more attractive, I have a set of slides that show also to the theorists who are not used to actually work on or something that can, break and have problems. I'm going to be talking about the bumpy road to dark energy, some of the hiccups, some of the problems that we saw, that we had along the way. So this was the first light. This was in 2019. We were super happy because we were the first of what we call the stage 4 dark energy surveys, basically the first of the competing surveys that we started taking data, and everything was working very well, and we were very excited. You can see here the focal plane of DESI. So every time we look at the sky, we cover a very wide range of scales, 38 times the full moon, said the video. And we had these 5,000 robots pointing at galaxies in that place and so on. And here, for instance, we just placed the fibers to a nearby galaxy, and we're able to obtain this beautiful optical spectrum, detect very emission lines, and so on, right? So the instrument was working great. We were all very happy. But then, as you know, we were having this meeting in Tucson. I arrived 1 week earlier because I was supposed to go to the telescope and observe. And at the end, I ended up having the meeting alone, only with 2 more people in Tucson, because we started seeing COVID everywhere, and we had to first cancel the meeting, but eventually also shut down the telescope for more than half a year. So this was the first problem, but of course, everyone in the room was also impacted by that. Then in May 2021, so basically a year after, we were actually able to again start the survey. And things went really well. Like, we started observing, so these are the 2 large areas of the sky that DESI will cover, and you're seeing here the observations every night. And we started accumulating a lot of data. The instrument was working beautifully. So this is after 1 year. We had already covered, I think it was 25%, right? So we were ahead of schedule. This is a 5-year program, but after 1 year, we had already done a quarter of the total survey. But then when we were celebrating, something else happened. There was a big fire, a wildfire right next to the telescope. And we were really afraid because it got really, really close. So this is taken from the webcam of the telescope. And by coincidence, there was another meeting in Berkeley at the headquarters of DESI, and we were all there. And we were refreshing the webcam, every few seconds just to check whether the fire was getting closer. At some point, the webcam went off. We all thought the telescope had burnt, but it was just the power. The power lines were down, so we just lost power. Luckily, there were around 50 firemen just surrounding the DESI telescope, so it was at the end fine. But other telescopes that were smaller and didn't have as many firefighters with them, they were severely damaged by the fire. So 3 months later, we went back and we started doing what we call the year 2. We collected a lot of good data. And then last summer, there was this news that there were hackers that attacked the Magellan telescope in Chile. So everyone panicked in the Neuer lab, who are taking care of several telescopes in the US, including our telescope in DESI. So we lost internet connection to DESI again because of this cyber attack. Luckily, it was not as long as the problem with the fire, but it again slowed us down significantly. The good news is that in spite of COVID, fire, and pirates, we are halfway through. So we are actually 3 or 4 months ahead of schedule because we have been quite lucky with the weather lately. You can see here how many millions of spectra, sorry, pointer 2, no, pointer 3. Point 3, okay. So this is the number of millions of spectra as a function of time. You can see here the first technical upgrades, then the fire, then the hackers. But we're already at 26.6 million, so we're going really, really well. And the first data that we already made public, it's called the early data release. I'm going to show one slide after this one about this. The first cosmological results, we call them DESI year 1 because of the first year of DESI data that we collected basically before the fire. And those were going to be released, the results will be released next year in 2024, so stay tuned. And then the final data set, year 5, will appear in 2020, we'll stop collecting it in 2026. The results will appear, a couple of years later. So the data that is already public, the first one is what we call the legacy survey, the imaging legacy survey, and that is because before doing the observations, we need to know where to put the fibers. We need to tell the robots, go look there and take a spectra of that galaxy. So first what we do is we do an imaging of the whole survey with just broad photometric filters without the spectra, only to identify the targets, and then we look at them with fibers. So the imaging data has been public for a couple of years. You can go there and take a look at it if you're interested. Then the early data release that is only containing data from the first few months when we were like debugging the telescope and debugging the pipeline and so on. With only a few months of data, we collected more quasars and more galaxies than previous surveys. So a million redshifts, but also including many stars. So even if you're not a cosmologist, if you want to do other type of astrophysics, there are many stars. Some of them we targeted them, some of them we observed by mistake. We thought they were quasars, but all those are also publicly available already since last June, I think, or last May. And this is a visualization from this early data release. Those are showing 20 pointings in the sky, and the data points here, the yellow points, are positions of actual galaxies that we have measured, and it shows you the idea is to basically cover a third of the whole sky with the same type of precision to have a very detailed map of the distribution of matter in the universe going to high redshift. So that's it. In summary, I hope I have convinced you that there's some fundamental physics questions that can be addressed with cosmology, in particular looking at this distribution of matter, and that dark energy can be constrained using both expansion of the universe and growth, and that combining cosmological probes is really important. The CMB alone, Planck, cannot study all these important extensions, cannot put limits on neutrino masses, or cannot put limits on curvature without other probes at low redshift like galaxy surveys. And as you saw, the dark energy spectroscopic instrument, DESI, is moving forward really well. So stay tuned, because it will soon provide the new state of the art in terms of neutrino masses, dark energy, curvature, and so on. And that's it. Thanks.
Questions? Come on, don't be shy.
Hi, thank you. Very nice talk. So if you confirm this W parameter to be like, to precisions less than 1%, and, everything still looks like lambda CDM, is there a future in cosmology for stage 5 experiments, or where do you see the actual future after all the DESI results and everything else?
It's a very relevant question. We are now designing the stage 5 experiments, and we're asking ourselves, is it worth it? Like, should we even bother? Because at some point, we'll get W measurements with a precision of 0.01% or whatever, right? It's like, we don't have a natural floor for when to stop, right? Similarly, you could say the same for curvature, although from the curvature, there are some models of inflation that you could actually get some natural lower floor where you would stop. But so there are some natural floors for curvature. There are definitely natural floors for neutrino masses. So we know that there has to be a minimum mass of some of the neutrinos. So in that sense, that becomes a more relevant target than dark energy. And then I haven't talked about this, but these galaxy surveys can also put very interesting constraints on inflation. For instance, looking at primordial non-Gaussianities. So there are some models of inflation that predict that even though the initial conditions should be very close to Gaussian, there should be some deviations. They also predict that the initial perturbation should follow a power law, but not quite. There should be some running, and there's some interesting consistency relations between the running and the primordial non-Gaussianities, and the amount also of primordial gravitational waves. So I think in the next few years, the next surveys will stop focusing on dark energy and will start focusing on neutrino physics and inflationary physics.
So, more questions? No more questions?
Thanks for the nice talk. So combining DESI results with other surveys like Euclid or LSST will improve constraints on neutrino masses or equation of state parameter?
Yeah, so So DESI will mostly look at this BAO to measure the expansion and this growth of a structure through these redshift space distortions. But there's another probe that is very interesting that is weak lensing. That is another way of looking at the growth of a structure, and LSST and Euclid will provide very good constraints from weak lensing. Euclid will also measure BAO, but I don't think it's going to be revolutionary to combine the two BAO measurements because it's just going to make a slightly smaller error bars. But the information that Euclid will bring on weak lensing measurements, that's going to be very relevant. So yes, you will improve the neutrino mass constraints and other constraints by combining weak lensing measurements with DESI measurements. And we can also cross-correlate them. So there's a working group in DESI that looks at cross-correlations of lensing with the galaxies. That will also be interesting.
So, more questions? No? So thank you again for a very interesting